Welcome to College Chemistry. Let me tell you who we think you are. We think that you are a college student or the equivalent majoring in a science-related field. We think your chemistry background is probably a good high school chemistry course or the equivalent, possibly an introductory chemistry course in college. And your math background, we think you have good algebra skills. Let's get going. What you will need for this course. You're going to need the DVDs, CDs, downloads, but if you're seeing this, you already have that. You should have a note guide. The note guide is a very, very quick, concise way to get an organized set of notes for this course. And when you need something like a periodic table, it's provided for you in the note guide. Or a table of oxidation numbers, it's right there. Or a problem written out, it is right there in the note guide. You will need a textbook. Now, if you're using this as a supplement to a course that you're already taking, you probably have a textbook, and that will be fine. However, if you don't, get one. Get one that is, 3 or 4 or 5 years old. You can get those used textbooks very inexpensively. You will need periodic tables, and we will provide them in the note guide. You will need table of oxidation numbers. Both of these, the periodic table and table of oxidation numbers, need to be that you can write on them, and they will be provided in that note guide. You're going to need a good scientific calculator. Now, it doesn't have to be programmable, and it doesn't have to be a graphing calculator, but it must have an EE or EEX or EXP key in order that you can do scientific notation, or some other way of doing scientific notation that does not involve 10 to the x power. Here, let's try a sample problem. Now, if you already know how to use your calculator thoroughly, you might want to skip over this. However, there might be something there. Consider this problem. 3.8 times 10 to the 15th times 8.4 times 10 to the negative 7th quantity divided by 1.7 times 10 to the third quantity squared plus 3.2. I'm going to show you how to input that into a typical algebraic calculator. If your calculator uses RPN, reverse Polish notation, you'll need to refer to your manual as to how to do this. Here we go. Input 3.8 and then use the EE or EXP or EEX key, whatever your exponent key is, but do not use 10 to the x. Put in this EE, then put in the exponent. You see, EE means times 10 to the whatever, already for you. Then put in multiply 8.4 EE, or whatever your exponent key is, 7, and then change the sign. If you put in your plus minus or your CHS key before you put in the 7, it may change the sign on the 8.4, and that's not what you want. Divided by 1.7 EE3 y to the x 2. That takes that quantity right there and squares it. Plus 3.2. And this thing follows the rule, my dear Aunt Sally, multiply, divide, add, and subtract. Yes. And that should equal, when you round it off somewhat, 1107.7. And we will get the significant digits straight when we get to that section. Well, enough on calculators. Let's get started. What is chemistry, and where did it all begin? Well, if you ask different chemistry historians, they very well may tell you different things. For some may tell you that it began after the era of alchemy. You remember alchemy? Have you read about it or heard about it? It's a fascinating phase of history in which you had people trying to change base metals into gold. And the question you have to ask is, why did they ever think they could do that in the first place? Did it begin with the Mesopotamian dye makers, those people who would work magic with colors in the dyeing of fabrics? Well, in any case, what is chemistry? You know that it's the study of matter and the changes that matter undergoes. And importantly, you also need to know that our knowledge of chemistry continues to change. We will briefly cover some terms we think you probably already know and mention a few that you might not be sure about. We'll talk about measurements, which you've probably heard forever. We'll talk about density and specific gravity, and then we'll do a quick review. But I want you to look over here on the left. And when you look on the left, you're going to notice that when we get to a certain section, for example, when we start on terms, you're going to see a check mark appear there. So at all times, you'll be able to look on the left-hand side and see precisely where we are in this particular unit. Terms you probably know. What about physical properties? These are properties or descriptions, physical descriptions, such as color, density, melting point, things of this type. Chemical properties talk about the kinds of reactions something might be inclined to undergo: decomposition when heated, reaction with oxygen, instability in an acid, things of that type. And what are physical changes? Well, physical changes are very often considered to be changes of state, when something changes from a liquid to a gas by evaporation or by boiling, when something freezes, things of this type. What about sublimation, folks? Well, sublimation is the conversion of a solid directly into a gas without appearing to go through the liquid state. For example, dry ice, which is solid carbon dioxide, sublimes, goes directly to the gaseous state. What about the way your frost-free freezer works? When you have things in the freezer covered with ice and the freezer blows dry air across them and the ice sublimes. And that helps keep the level of ice accumulation down. Well, what about chemical changes? Chemical changes, of course, are chemical reactions that things undergo. Things that produce a new material with a new set of chemical and physical properties. What about elements? Do you know the elements? You know that there are a lot of them, and there are some that have been added. We'll talk more about these shortly. And then, of course, there are compounds, which are atoms bonded together in a very, very specific way to form collections that we call compounds. There are several terms we need to review and make sure we're on the same page. Substances, intensive and extensive properties, homogeneous and heterogeneous mixtures, atoms and their symbols, molecules and their formulas. Now we're going to take a minute and look at each of these individually. Let's start with substances. Substances happen to be matter having a fixed composition that doesn't vary. If you have a particular substance, it doesn't matter what your source of that substance is, where you find it, or in what part of the sample you examine, the composition is fixed. It doesn't vary. So that means substances are limited to elements or compounds. Intensive properties. What are intensive properties? Intensive properties are independent, intensive and independent, properties that are independent of the amount used. It doesn't matter whether you use a microgram or whether you use 3 metric tons. These things don't change. For example, density, melting point, and chemical reactivity. So intensive properties are properties or characteristics that have no relationship to the quantity of the material that is used. What about extensive properties? Well, extensive properties are dependent on the amount of material that you're using. Some examples: the volume. The volume is definitely dependent on how much you use, as is the mass. What about the quantity of heat needed to raise the temperature of the sample? It's a lot of difference between the amount of heat needed to raise the temperature of a half a gram and the amount of heat needed to raise the temperature of 5 metric tons. Yes, These are extensive properties. Homogeneous mixtures, sometimes called homogeneous, but I believe the more common pronunciation is homogeneous. These are mixtures that appear to be a single substance. You cannot visibly discern where one material stops and the other material starts. In other words, it appears to have one phase. Saltwater solution is a good example. The homogeneous mixture will have a constant composition throughout. It will have a constant composition throughout. An alloy is an example that has a constant composition throughout the sample. There's another name for homogeneous mixtures. Homogeneous mixtures are also known as solutions. Even though they are not liquid, they can be solid, they can be gaseous, they can be any of the combinations of the states of matter. Heterogeneous mixtures, however, are mixtures whose composition varies within the same sample, and you can usually look, or not usually necessarily, but you can often look at a heterogeneous mixture and see where one material stops and the other material starts. In other words, a heterogeneous mixture will have more than one phase. How about oil and water? Shake it up and you can begin to definitely see the two phases, can't you? What about peanut butter and iron filings? Now, you may not be able to see it, but your teeth will certainly be able to distinguish where the peanut butter ends and the iron filings begin. Atoms and their symbols. Now, you've been taught about atoms and their symbols since you're knee-high to a bottle stopper, and you know that atoms are the smallest part of an element. Well, for our purposes, there are 111 elements. And the symbols are going to be one or two letters. The first letter is always capitalized, and the second letter is always lower case. Now, it's important that you remember that's lower case. Let's look at some. Let's see, how about calcium? It's C with a lowercase a, not C with a shrunken capital A. You can't use a shrunken capital in there, it won't work. But it's two letters. Nitrogen, however, only has one letter. And then, of course, there are some odd ones. That don't necessarily make sense, like calcium and nitrogen too. For example, there's Pb, lead. Lead. It comes from plumbum. Fe, iron, comes from ferrum. Na, sodium, comes from natrium. And so forth. You're going to have a number of these. And I want you to learn them all. Learn all 11 elements and their symbols. And I suggest you use flashcards. Put the name on one side, the symbol on the other. Carry a stack of 10 or 15 around with you. Change them out regularly. And you will find you can learn them very painlessly in a very quick amount of time. There are some for which you may wish to hear the names pronounced. Fluorine is an example. It's often pronounced fluorine, but I believe the preferred pronunciation is fluorine. Americium, americium. This one sounds like you run into a wall and fall off. Molybdenum, molybdenum. This one looks tough, but it's really pronounced phonetically. Praseodymium, praseodymium. Here we have technetium and neodymium. Let's move on. Molecules and their formulas. What are molecules and their formulas? Well, a molecule is the smallest part of an element or a compound when two or more atoms are bonded together. Now, folks, are you surprised that I put element in here? A molecule can be the smallest part of an element. It can be the smallest part of the element that occurs naturally. For example, Do you remember the 7 diatomic elements? Sure. Hydrogen, fluorine, chlorine, bromine, iodine, nitrogen, and oxygen. The 7 diatomic elements. When they occur naturally, they occur as 2 atoms bonded together, and they're called the diatomic elements. Sometimes you're going to find sulfur written as S8. It depends on what form the sulfur is in, but it is not uncommon to find sulfur with 8 atoms to make up a molecule. And phosphorus. Phosphorus is sometimes indicated by P4 when there are 4 atoms making up a molecule of phosphorus. In this part of the unit, we're going to talk about the metric system, specifically the prefixes that are used and what the correct way is of using them. We'll talk about temperature and how the scales came about. We'll mention how to manage numbers and talk about a particular calculation method that you will find us using a lot throughout this course. We must be able to make measurements in chemistry, and we must have a way that is consistent of doing it. We must be able to measure length, volume, mass, temperature, and time. And we must do this using the International System. But first, let's look at the metric prefixes. These are the ones you need to know. 10 to the 9th is giga. Now, we generally use a lowercase g, but you may see it as a capital G. And mega, 10 to the 6th, must be a capital M. Kilo, you may see it as a lowercase k, which I think is now becoming preferred, or you may see it as a capital K. The thing about it having a capital K is we don't want it to be confused with Kelvin, the temperature scale. Deci is a lowercase d, centi is a lowercase c, milli is a lowercase m, and it is the existence of milli that forces us to use a capital M for mega, so that we can distinguish between mega and milli. Micro is using the Greek number, the Greek letter. Nano is a lowercase n. Pico, or pico, is a lowercase p. And femto is a lowercase f. You're going to find that the more modern textbooks and the more modern resources are going to use the lowercase letters, except in the case of mega. But that really doesn't bother us very much because we don't use mega very much in chemistry. That's getting to be rather large. Length. The International System for length is the meter. And there's an equality that you should know. You should know that 2.54 centimeters is exactly equal to an inch. As many zeros as you want to put past that, because that is an absolute equality. Exactly. For volume, the standard unit is the cubic meter. Now, ladies and gentlemen, the cubic meter is huge. A cubic meter is larger than 27 cubic feet. And in chemistry, that gets to be a little unwieldy. So what we do is commonly use the cubic centimeter, which is exactly equal to a milliliter. Now, if you happen to look back on some of the older references, you may notice that a cubic centimeter and a milliliter are not the same in those references. The correction was made in 1964, but prior to that, they were not the same because Bechêne and Delambre, who were the surveyors who helped determine the unit of length called the meter, made an error, and therefore the cubic centimeter was off, and hence the milliliter was off. Well, anyway. Know that since 1964 that a cubic centimeter is equal to a milliliter, and also understand that it took several years for it to hit the books. Well, let's go on. A cubic decimeter is equal to a liter. Now, a liter, you will hear, is the old metric term, but let me assure you in chemistry, we use it a lot. And there's an equivalency I want you to know. I want you to learn that 946.4 milliliters is equal to a quart. You may see this as 946.3, but I believe that the corrected value is 946.4 milliliters is equal to a quart. Mass. The SI unit of mass is the kilogram. But in chemistry, we don't use the kilogram as much as we use some smaller units of mass. So in chemistry, you're going to find we commonly use the gram and the milligram. And there comes up another relationship that you need to know, and that is 453.6 grams is equivalent to a pound. 453.6 grams is equivalent to a pound. Thus, a kilogram is about 2.2 pounds, but that is not as accurate as the 453.6 grams in a pound. Now, we talked about mass, and we've mentioned some weight, but what's the difference between mass and weight? Well, weight is a measure of gravity, and as gravitational pull changes, so does weight. On the other hand, mass is a measure of inertia and is constant. Mass is not dependent upon gravity as far as we're concerned. It is a measurement of inertia, a body's resistance to changing its position, or a body's resistance to being moved. And it is constant. Temperature. What is temperature? Well, temperature is not quite proper to say it's how hot or how cold something is. It's a relative hotness or coldness. And how do we measure it? We measure it by comparing it to a standard. Now, the SI unit for temperature is Kelvin, but in chemistry we use Fahrenheit and Celsius also. Therefore, it behooves us to make sure we understand all three of these scales: Kelvin, Fahrenheit, and Celsius. Consider the scales we commonly use in chemistry. We use the Fahrenheit scale, the Celsius scale, and the Kelvin scale. Now notice that we use degrees Fahrenheit, degrees Celsius, but we refer to kelvins just as kelvins or units Kelvin. Water boils and water freezes are 2 points that we really should consider on all three scales. On the Fahrenheit scale, water boils at 212 degrees Fahrenheit and freezes at 32. This means that water exists as a liquid over a range of 180 units on the Fahrenheit scale. On the Celsius scale, water boils at 100 degrees Celsius and freezes at 0. So water exists as a liquid over 100 units on the Celsius scale. For Kelvin, water boils at 373 and freezes at 273 kelvins. So once again, water exists over a range of 100 units on the Kelvin scale. Therefore, it takes 100 units to describe the existence of water as a liquid on two of the scales, Celsius and Kelvin. But Fahrenheit requires 180 units for that same description. Therefore, it takes more units on the Fahrenheit scale to describe a change than it does units on the Celsius or Kelvin scale. Thus, a unit change on the Fahrenheit scale is a smaller change than is a unit change on the Celsius or Kelvin scale. Now, I want you to notice where the scales begin. If we talk about 0 as being a beginning point, 0 on the Celsius scale is where water freezes or ice melts. Well, what about 0 on the Kelvin scale? 0 on the Kelvin scale is thought to be the temperature at which all molecular motion ceases, and we often refer to that as absolute 0. The Fahrenheit scale, what happens at 0 on the Fahrenheit scale? The Fahrenheit scale is a fascinating scale. It has an interesting history. At 0 on the Fahrenheit scale, there's a certain saturated salt solution that will freeze at 0. And that's the way the 0 was determined for the Fahrenheit. Let's stop and look at some history on the Fahrenheit scale. In 1724, Daniel Gabriel Fahrenheit invented a new thermometer. He had been working with the alcohol thermometers, which were the ones being used in that time, but they were inadequate for the range of temperatures that he needed. So he decided that he needed a thermometer with a liquid that would withstand a broad range of temperatures, like mercury. And so he built a mercury thermometer. Now, he has this thermometer, and oh yes, it has a broad range. But what is he going to use for his scale? Where is he going to set 0 on this thermometer? So he decided to take a page from Romer, the Danish astronomer, who sincerely felt that nothing could ever be colder than the coldest day in Denmark. And so he decided to use that as his beginning point on the scale. And he later found that a mixture of ammonium chloride and water would have a freezing point very similar. And so he set out his thermometer, and the coldest day there was, he marked that as 0, and yes, that was like that solution of ammonium chloride. Okay, now he has 0 on his scale. What shall he use as his next point? He decided to test out a theory of the day, and that was that pure water froze at a variety of temperatures. It froze at a variety of temperatures depending on the conditions of the day. And so he checked it out. He froze pure water. Marked that on his thermometer. Tried some pure water under different circumstances, still freezing it. Marked that on his thermometer. They were the same. He continued to test the freezing point of pure water and discovered it was always the same. And so he set that as his second point on his thermometer. Now he has 0, and he has a second point. But how shall he separate his units? What values shall he use on his scale? So he wanted to use a number that was divisible by a number of numbers. And so he chose 2 to the 5th power. That's 32. And so he marked that freezing point of water, pure water, on his scale as 32 degrees. Now he has 2 points. What shall he use for his third point? So he decided to try out something. He put the thermometer in his mouth. Noted that position. Put the thermometer under his arm. Noted that. They were the same, or close enough. Put the thermometer in his wife's mouth. Yep, same. And under her arm. And so he determined that body temperature was this particular point on his scale. And he noticed that was about twice the distance between 0 and his 32, freezing point of water. And so he marked it as 2 to the 6th power distance. Now, 2 to the 6th power is 64. Plus 32 makes 96 as his determination of body temperature. And so he has his 3 points, 0, 32, and 64 on his, 96, on his scale. Now granted, scientists later went and tweaked that body temperature a little bit because we now know that it is closer to 98.6 on the average. But that is the way he set up this new thermometer. Let's look at the relationship between degrees Fahrenheit and degrees Celsius. Remember, 180 units on the Fahrenheit scale are required to describe the same change that you see only 100 units on the Celsius scale being needed. Therefore, the relationship between Fahrenheit and Celsius degrees is that Celsius takes 5/9 as many degrees to describe something as Fahrenheit. Now, to the contrary, if you're converting or relating Fahrenheit and Celsius, a Fahrenheit degree takes 9/5 as many units on the Fahrenheit scale as it does on the Celsius scale. It takes 180 units on the Fahrenheit scale when it only takes 100 units on the Celsius scale. The Celsius degree, or the Celsius unit, is a larger unit than the Fahrenheit unit, so it takes more Fahrenheit units than it does Celsius units. But now if you're going to convert a particular temperature, you have to look at it a little differently. Remember, you have to then consider where the scale starts. And degrees Celsius, if you're converting from degrees Fahrenheit to degrees Celsius, degrees Celsius then is 5/9 of the difference between the Fahrenheit scale and 32. In other words, you've got to drop that scale down 32 units. And the Fahrenheit scale, take 9/5 of whatever units you have with C and add 32 to that value, and that will give you the corresponding temperature on the Fahrenheit scale. The relationship between degrees Celsius and kelvins is very straightforward. You will notice that there's 100 units to describe the existence of water on the Celsius scale as a liquid, and 100 units for the Kelvin scale. Oh, note one other thing. I've been very happily talking about 373 kelvins and 273 kelvins. Technically, it's 373.15 and 273.15. And if you really want to be correct, you will use all 5 significant figures. However, you will very often hear people just referring to 373 and 273 instead. Well, anyway, let's look at the relationship. A degree change on the Celsius scale is equivalent to a unit change on the Kelvin scale. They just are at different points in the number system. Degrees Celsius is K minus 273.15 or K minus 273. And Kelvin is degrees Celsius plus 273.15, which you may see as degrees Celsius plus 273. Very straightforward and very simple. Straightforward problem in which you're asked to convert 35 degrees Celsius to degrees Fahrenheit. And it's relatively simple if you remember the formula. Do you remember the formula that degrees Fahrenheit is equal to 9/5 times degrees Celsius plus 32? Do you recall that the 9/5 comes from 180 over 100 being reduced to 9/5? And the 32 comes from where the scales start, because the Celsius starts at 0 and the Fahrenheit starts at 32. Well, anyway, degrees Fahrenheit is equal to 9/5 times 35 plus 32. Now let's see, 9/5 of 35, 5 going to 35, 7 times 9, 63 plus 32 is going to be 95 degrees Fahrenheit. All right, that's pretty straightforward. Now, what would you do with this one? What if instead of being asked for a specific temperature, and that's something you need to remember up here, that this is a specific temperature we're asking for up here. But what if you aren't being asked for a specific temperature? What if you were asked, if the temperature changes by 25 degrees Celsius, what would it change in degrees Fahrenheit? And in that case, ladies and gentlemen, that is not a specific temperature, that is a range. Now, if it's a range of temperatures, we don't care where the scale starts. All you have to know is the relationship. 9 degrees Fahrenheit for every 5 degrees Celsius. So you can do this a couple of ways. You can say, all right, I'm going to take 9 degrees Fahrenheit over 5 degrees Celsius times 25 degrees Celsius. My Celsius degrees will cancel. And I will have 5 will go into 25. 5 times 9 is 40. 5 degrees range on the Fahrenheit scale. That's one way to look at it. Another way to look at it is like this. If it's going to change 9 degrees on the Fahrenheit scale for every 5 degrees on the Celsius scale, then how much is it going to change on the Fahrenheit scale for 25 degrees on the Celsius scale? And you'll come up with the same answer. X will be equal to 45 degrees on the Fahrenheit scale. But you have to remember that's a range. That's a range like 10 degrees to 55 degrees, or a range like 32 degrees to 77 degrees. That's right. So keep those differences, range and specific temperatures, straight in your thinking. A better way to teach and learn chemistry.